Why is quantum mechanics so hard to understand? Imagine trying to follow a recipe where the ingredients keep changing shape and size, and you cannot see the full picture. That's what makes quantum mechanics so puzzling. It challenges everything we know about how the universe works at the smallest scales. Back in the early 1900s, scientists faced strange problems. They needed to explain blackbody radiation and the photoelectric effect. These issues led to the idea that energy is not continuous but comes in tiny packets called quanta. Max Planck introduced this idea in 1900 to explain blackbody radiation, but he was hesitant to accept its full implications. Later, Albert Einstein showed that light itself is made of particles called photons, which can behave both as particles and waves. This was a huge shift from classical physics, which saw light as only a wave. Niels Bohr then created a model of the atom where electrons move in specific orbits, or energy levels. These orbits are quantized, meaning electrons can only exist in certain places. But his model still used ideas from classical physics, just with added rules. Werner Heisenberg in 1925 developed matrix mechanics, a very abstract way to describe electrons. Instead of picturing electrons moving, he focused on what could be measured, like spectral lines. Soon after, Erwin Schrödinger introduced wave mechanics, describing particles as waves called wave functions. But at first, scientists didn't understand what these waves really meant. Max Born later explained that the wave function predicts probabilities, not certainties. This means we can only know the likelihood of finding an electron in a certain spot, not its exact position. This shift from definite paths to probabilities is one reason quantum mechanics is so tricky. It also relies on complex math, like matrices and wave equations, which are not intuitive. Plus, the Heisenberg uncertainty principle states that you cannot know both an electron's position and its momentum at the same time with perfect accuracy. That goes against what we experience in everyday life. Quantum phenomena also don't have real-world analogs. Experiments like the double-slit show particles interfering with themselves, which makes no sense in classical terms. These strange behaviors forced scientists to rethink what matter and energy really are at the atomic level. Despite its difficulty, quantum mechanics has led to amazing technologies like computers, lasers, and MRI machines. It shows us that the universe is more complex and surprising than our everyday experience suggests. So, it's hard to understand because it overturns our common sense ideas, uses abstract math, and describes phenomena outside normal perception. Its history is full of key discoveries that gradually changed how we see the tiny building blocks of everything around us.